Yes. Hello, everybody. How are you? I think and I hope all of you are well and good. So, let's start today's lecture. Today, we are going to revise or do revision of manufacturing process to throw previous year question. Right? Throw previous year question. So, let's start. Today, we are going to cover theory of metal cutting, tool life, NTMM, welding, machine tool, NCCNC, and additive manufacturing. So here's the first question. Here is the first question. So please solve this question. Yes, please solve this question. In this question, it is mentioned that a single point turning tool side rake angle and orthogonal rake angle are equal, right? Lambda is a principal cutting edge principal cutting edge angle whose range is 0 to 90 degree. The chip flow in orthogonal plane, we have to find the value of what? Lambda, that is principal edge cutting angle, right? Principal edge cutting angle. Okay. Now here it is given that side rake angle, that is alpha s equal to alpha, and chip flow in orthogonal plane, so inclination angle is 0. Here we have to find out the lambda, right? So side rake angle equal to orthogonal rake angle. So here what we do, we can apply tan of side rake angle equal to, right, tan of side rake angle equal to tan alpha sin lambda, tan alpha sin lambda minus cos lambda tan I, minus cos lambda tan I. Here the chip flow in orthogonal plane, so I is 0, so this term got 0. Tan of alpha s equal to tan of alpha sin lambda. Alpha is equal to alpha, so this will cancel out. Now sin lambda equal to 1. So the value, okay, sin lambda equal to 1, okay, according to this range, lambda should be 90 degree. So answer is option D, right? Answer is option D. Now the next question. Now the next question. During orthogonal cutting of mild steel, rake angle is 10 degree. Rake angle is 10 degree. The chip thickness ratio was obtained, that is 4. Shear angle we have to find out. So tan phi equal to r cos alpha divided by 1 minus r sin alpha. Phi equal to tan inverse r, that is 0.4 cos of 10 divided by 1 minus 0.4 sine of 10. So here you will get the shear angle. Here you will get the shear angle, 0.4 into cos 10 divided by 1 minus 0.4 into sine 10. So 22.94 degree. 22.94 degree. So the correct answer is option C. Next. Detail pertaining to an orthogonal metal cutting whose chip thickness ratio R is given, undeformed thickness T0 is given, rake angle alpha is given, cutting speed is given, mean thickness, that is shear zone thickness, is given, shear strain rate. So shear strain rate is shear velocity divided by thickness of shear zone. Thickness of shear zone is given, right? That is 25 microns. But we don't have the shear velocity. And for a shear velocity, we need a shear angle also. So phi equal to tan inverse R, that is 0.4 cos alpha, right, divide by 1 minus 0.4 sin alpha. Is it clear? Is it clear? So here I think 0.4 into cos alpha divide by 1 minus 0.4 into sin alpha, shift to 10, yes, 0.4 into cos alpha, answer divided by 1 minus 0.4 into sin alpha, shift 10 inverse, that is phi is 22.94. Now here is the velocity triangle, that is cutting velocity, shear velocity. This is 90 minus alpha, this is phi, this is 90 minus phi minus alpha. So Vs divide by cos alpha, V divide by cos of phi minus alpha. So here you will get the Vs. So the Vs, V is what? 2.5. So 2.5 cos of alpha, that is 10, cos of 22.94 minus 10. So cos of 10 divided by cos of phi minus 10, answer into 2.5. So here the shear velocity is 2.526 meter per second. Meter per second. So cutting shear strain 2.526 meter per second, 25 micron, 25 into 10 to the power minus 6. So answer divided by 25 into 10 to the power minus 6. So here it comes 1.01048, okay, into 10 to the power 5, 10 to the power 5 per second. Option C is the correct answer. Next question. A built-up edge is formed while machining. Built-up edge is formed while machining ductile material at high speed, ductile material at low speed, brittle material. Brittle material, built-up edge will not form. Built-up edge will not form. Built-up edge will form only when you do a machining of ductile material, but at low speed. So option B is the correct answer. In orthogonal turning of a low carbon steel of a diameter uncoated, the cutting velocity, the feed is given here. The feed is given and the depth of cut is 2 mm. The chip thickness obtained 0.48. If the orthogonal rake angle is 0 and primary cutting edge angle is 90 degree, the shear angle in degree. So turning is a process. So uncut thickness is f sine lambda. So T naught f is what? 0.24, 0.24, right, mm. Sine lambda, here lambda is what? 90 degree, and here is the r, that is T naught by Tc. T naught is 0.24 and Tc is 0.48, so it is 0.5. Phi equal to tan inverse r cos of 0, right? Rest of the thing 1 minus 0. So shift tan inverse 0.5. So phi become 26.565. 26.565, option B, right? Next. During orthogonal machining of a mild steel specimen with a cutting tool of 0 rake angle, here cutting tool of 0 rake angle, uncut chip thickness T naught is given, chip thickness Tc is given, width of cut is given, normal force is given, and thrust force is given. The shear angle and shear force respectively. So shear angle, that is 10 inverse R, that is 0.25, 0.25 divided by 0.75. So here R is 0.25 divided by 0.75, and it is 0.333, right? So 0.333 cos of 0, 1 minus, okay, 1 minus 0.33 sine of 0. So shift and inverse answer. So 18.434 degree is the shear angle, right? Is the shear angle. So here you can see we are getting 18 point something here. So directly you can take this, okay, and you can calculate this also if you want, right? Then how can we calculate? We need what? Shear force. Shear force is what? FC cos phi, remember or not? FC cos phi minus FT sin phi, minus FT sin phi. Remember or not? Fn and Fs. FC cos phi minus FT sin phi. Here Ft is given, but Fc is not given. You know that when alpha equal to 0, then normal force become equal to what? Fc. So Fc is what? 475. 475. So you can put here Fs 475 cos of 18.434 minus 475. Sorry, it is not a 475. Normal is 950. 950. Right here, 950 cos of 18.434 minus 475 sine of 18.434. So 950 into cos of phi minus 475 into sine of phi. So here comes 751, 751.04 Newton, that is Fs, right? That is Fs. Next question. We have to find during orthogonal machining of mild steel specimen cutting of zero rake angle. Here data is same, everything is same. We have to find ultimate shear stress. Everything is same. We have to find ultimate shear stress. We know that ultimate shear stress is Fs by As, right? And shear plane area is WT naught divided by sine phi. Width of cut 2.5 mm. So 2.5 mm. T naught is 0.25 mm. 0.25 mm divided by sine of 18.434. Now we have the value of Fs 751.04. So tau naught 751.04 divide by W 2.5 into 0.25 into sine of 18.434. Answer into sine of 18.434. Answer divide by 2.5 into 0.25. So here it comes tau naught 379.9811 Newton per mm square, right? Newton per mm square. So 379, nearby option is D. Next, in orthogonal turning a carbon, specific cutting energy is given, that is 2 joule per mm cube. The cutting velocity, speed and depth of cut are given. The main cutting force, we know that a specific, okay, cutting specific energy is work done divided by MRR, right? So work done, that is cutting force into cutting velocity, divide by MRR, because it is a turning, so we can write FdV. You cannot cut velocity directly because the unit of velocity is different, right? So here cutting force velocity is 120 divided by 60 meter per second, divide by feed, that is 0.2, into depth of cut is 2, divide by V. So here 120 divided by 60 meter per second, here it will be in mm per second, so 1000. Now specific cutting energy is what? 2. So here we will get what? We will get our cutting force, that is 800 Newton. 800 Newton. Is it clear? Next, the coefficient of friction we have to find out. So mu equal to F by N, that is Fc sin alpha, Fc sin alpha plus Ft cos alpha divide by Fc cos alpha minus Ft sin alpha. Is it here? Here alpha is given, right, and cutting force and thrust force is given. So mu equal to Fc. Here we need to write the Fc. Fc is what? Cutting force 1200 sin alpha. Alpha is what? 15 plus Ft, that is 200 cos of what? 15. 1200 cos of 15 minus 200 sin of 15. So here 1200 into sin of 15, right, plus 200 into cos of 15. Answer divide by 1200 into cos of 15 minus 200 into cos of sin of 15. So 0.45. So here mu will be 0.454. Here mu will be 0.454. So 0.46 is the right answer. Now, in orthogonal machining operation, uncut chip thickness is given. He want percent of total energy dissipated to the friction. Means energy, right, which is dissipated in friction versus total energy into 100. So we need to find the friction force, that is Fc sin alpha plus Ft cos alpha, right? And we need to find the chip velocity also. Okay, so but I think there is no requirement here. See, here we can write that friction into chip velocity divide by cutting force into cutting velocity into 100, right? We can write F friction force is Fc sin alpha 15 plus Ft 200, okay, plus Ft, okay, Ft cos 15 into chip velocity divide by cutting force, that is 1200 into cutting velocity. Now chip thickness ratio, right? Uncut thickness, that is T naught by Tc. So uncut thickness is 0.5 and chip thickness is 0.7. So it is 5 by 7 and it is also equal to VC by V. So here we can write that FC is 1200 sine of 15 plus 200 cos of 15 divide by 1200 VC by V. We can write 5 by 7, right? 5 by 7 into 100. So 1200 into sine of 15 plus 200 into cos of 15, answer divided by 1200, answer into 5 by 7, answer into 100. So option A, that is 29.986%. Okay, clear? What happened? B or A? B or A? In front of you, 29 point something is coming. How can you say the B is the answer? Now it is the same question. Now here the value of shear angle and shear strain respectively. So shear angle phi equal to tan inverse R, that is 5 by 7 cos of alpha divide by 1 minus 5 by 7 sine of 50. Okay, so 5 by 7 answer into cos of 15 divide by 1 minus answer into sine of 15, shift tan inverse answer. So here phi is 40.245 degree. Now shear strain, that is cot phi plus tan of phi minus alpha. So cot phi, that is 40.245 plus tan of 40.245 minus 10. So here sorry, it is 15, right? 15. So 1.65. 1.65. Option D. Now, which pair of the following statement is correct for orthogonal cutting using a single point cutting tool? So here we need to apply merchant analysis, right? Reduction in friction angle. If you reduce the friction angle, then cutting force increases. My dear, if you reduce the friction angle, then phi is increases, which implies that shear plane area decreases, which implies that required shear force decreases. So how can you say that increase in cutting force? Here reduction in friction angle, right? This will be right. Reduction in friction angle, decrease in cutting force. Reduction in friction angle, increase in chip thickness. No. If you reduce the friction angle and if phi is increases, then the chip thickness is decreases. So Q and S, that is option D. That is option D. During machining the wear, here I hope this data is visible to you. 0.8, 2.0, that is a roughness in mm. This is 10, this is 60, tool life in minute, right? Now he wants to calculate the tool life when the roughness become 1.8. So it is obvious that 1.8 comes nearby here, right? So the corresponding tool life is T and this is 1.8. So first we find out the tool life, right? 1 and 2 linear equation, that is y2 minus y1 divided by x2 minus x1, y minus y1 divided by x minus x1. y2 is 2 minus y1 is 0.8 divided by x2 is 60 minus x1 is 10. Y, that is 1.8 minus y1 is 0.8, x, that is t, minus x1 is 10. So from here you will get t, that is 2 minus 0.8 divided by 60 minus 10, right? And answer into 0.8, right? I think something is wrong. Kya? Something is wrong na? I did the wrong calculation. I did the wrong calculation. This is basically what 10 comma 0.8, and this is 60 comma 2, right? So here y2, that is what 2 minus 0.8, 2 minus 0.8, x2 60 minus 10, 60 minus 10, y, that is 1.8, 0.8 divided by x, that is t minus x1, that is 10. No, everything is perfect. 2 minus 0.8 divided by 60 minus 50, right? Then t minus 10. Then here 1 divided by this, answer plus 10, 51. So here it comes 51.66 minute. So 51.66, 51.66. So option B is the right answer. Taylor's tool life exponent n and constant. Similar for Taylor tool life B, the cutting speed above is tool A will have a higher tool life. Here V t to the power n equal to C, T equal to C by V to the power 1 by n. If you select the tool 1, then tool life will be C1 by V. In both the case, tool life is, in both the case, velocity is equal, right? In both the case, he is asking that velocity, which is common in both the cases, right? At which tool life 1 has a higher tool life than tool life 2. So C2 by V divide to the power 1 by N2. So T1. So what is C1? 90 divided by V to the power 1 divided by 0.45, right? Greater than equal to, that is 60 divided by V to the power 1 divided by N2, that is 0.3. So can you please tell me the value of V? Can you please tell me the value of V? We need to find that velocity at which tool life 1 has a higher tool life than 2. So what is the tool life? What is the velocity in that case? Here 90 divided by to the power 0.3, 60 divided by to the power 0.45, shift solve equal. How much you are getting? Yes. How much? 26.66. 26.66 meter, okay, per minute. Meter per minute. So option A is the right answer. A cylinder of 25 mm a cylinder of 25 diameter and 100 length is turned with a tool for which the relation is this. If the relation is not visible, then Vt to the power 0.25 equal to 55 is applied. The cutting velocity is 22 meter per minute for a tool feed of that much. The number of tool regrind to produce 425 cylinder. So what to do? First of all, we need to find the machining time. So here, machining time of one cylinder, right? Machining time of one cylinder, that is L divided by Fn. So length of the cylinder is 100 divided by, okay, here RPM is not given. So cutting velocity V equal to pi dn divided by 1000 meter per minute, that is 22. So it will give you the RPM, right? So it will give you what? RPM. So 22 into 1000 divided by pi into d. So 70.028 RPM, revolution per minute. Is it clear? 2200 pi d. Now machining time of one tool, that is L divided by Fn. Right. Machining time of one workpiece. Tool regrind required to produce. Now for 425 total machining time, that is 425 into T1. So 425 into T1, L, that is 100 divided by F 0.046, 0.046 into N, that is 70.028. So here 100 divided by 0.046 into 70.028. Answer into 425. So that much time is needed, 1319.3.48 minute. This is a total time. Now tool life, Vt to the power 0.25 equal to 55. Here 55 divided by V, that is 22 to the power 1 divided by 0.25. What is that? Here 55 divided by 22 to the power 1 divided by 0.25, that is 39.0625, right, minute per tool. Then we need to do a service. So number of tool, that is this divided by this. So 13193.48 divided by, so 337. Something is wrong. Yes. Did I wrong something? Oh, ho. I put the wrong diameter value. That's why. My God. Here diameter is this. This is length. I put V, that is 22, pi d, that is 25, n, divide by 1000. So here comes the RPM. Oh my God. 22 into 1000 divide by shift pi into 25. So RPM is 280.1126 RPM. Machining time of one workpiece, right, that is L divided by Fn for 425 cylinder. Total machining time 425 into L divided by Fn, that is 425 L, that is 100 feet 0.046 into 280.112, right? So here answer multiply, right, 100 divided by, yes, 100 divided by 0.046 into RPM, answer 425. So 3298.361 minute, right? And the tool life Vt to the power 0.25 equal to 55. Here the tool life will be 55 divided by 22 divided by 22 to the power 1 divided by 0.25, that is 55 divided by 22 to the power 1 divided by 0.25, it is 39.0625. Now number of tool regrind, that is 3298.361 divided by, so 84.438, so 85. Here from where it come, 3298.361 divided by 39.0625. From where it come? It comes T divided by tool life. Number of tool regrind. Number of tool regrind. Regrind. Is it clear? Is it clear? Not 87. Others Kumar 87, not 87, it is 85, right? Oh, same work, same question again repeated. Now, if the Taylor's tool life exponent n 0.2 and the tool changing time 1.5, then the tool life for maximum productivity. So it is Tc 1 minus n by n, Tc 1.5, 1 minus 0.2 divided by 0.2. 1.5 into 1 minus 0.2, answer divided by 0.2, so 6 minutes per 2. Clear? Now, in an electrochemical machining operation, a square or over dimension, this is this. The current used is 500 ampere. Atomic weight of the copper 68. Valency of dissolution 1. Faraday constant this. The material removal rate. So here the material removal rate is I E divided by F. I is 5000, E is 63 divided by 1, 96500 gram per second. So 5000 into 63 divided by 96500, so 3.264 gram per second. Next, while material removal rate, atomic weight is this, valency is this, density is this, MRR is this, the required current you have to find out. So material removal rate, that is 2 centimeter cube divided by 60, then it is per second. 2 centimeter cube per minute is there, na? So 2 by 60 centimeter cube per second. I E divided by Faraday into density. So I E 56 by 2 divided by 96500 Faraday. Density is 7.8. So you will get the required current, right? Nearby 896. 2 by 60 into 96500 into 7.8. Answer divided by 56 by 2. that is 896. 896.07 ampere. Okay, next, the percentage of metal P. So here you can see that there is a alloy, right, binary alloy of metal 1, that is iron. This is metal 1, and there is a metal 2 which is P, right. Overall composition is 100%. He wants to know the percentage of P. So we assume X percent of P. Then iron will be 100 minus X percent. Right. MRR is given here, binary alloy. Okay. Here binary alloy. So binary alloy density is given. Alloy density is given 6000 kg per meter cube. That is 6 gram per centimeter cube. So MRR is E equivalent. Here MRR is given or not? Something is, yeah, MRR. E equivalent into I divide by F into rho equivalent. MRR is 50 mm cube per second. So 50 into 10 to the power minus 3 centimeter cube per second, E equivalent into I, that is 2000 divided by 96500 into rho, that is 6. So from here we will get the equivalent. So 50 into 10 to the power minus 3 multiply 96500 into 6, answer divided by 2000, that is 14.475 gram per mole. We know that 100 by E equivalent equal to percentage of metal 1, that is 100 minus X divide by 56 by 2, 56 by 2 plus percentage of metal 2, E of metal 2, that is 24 by 4, 24 by 4. Now we know the value of E. Put here, you will get the X, that is 25.6, I think 25.6%. So nearby option is B. Clear? Nearby option is B. Clear? Now next question. Here, electrochemical machining. Okay, we need to find the material removal rate. So material removal rate in gram per second, that is E, I divide by F, gram per second. We need the E, but we don't have the value of I. So current density, that is I by cross-sectional area into S, okay, V naught minus delta V by Y. Here current divided by cross-sectional area is 20 mm cross 20 mm. So can we write 2 into 2, right? That is 2 into 2 centimeter square cross-sectional area, because here specific resistance is given 2 ohm centimeter. So 2 V naught applied voltage 12, drop voltage is not given, inter-electrode gap 0.2 mm. Can we convert it? 0.02 centimeter. So 0.02 centimeter. So from here we will get the current. 12 divided by 0.02, answer into 4 divided by 2, that is 1200 ampere. Now put here material removal rate, that is E, atomic weight 55.85 divided by 2 into I, that is 1200 divided by 96500. So 55.85 divided by 2, okay, into 1200, answer divided by 96500. So here comes the MRR 0.347 gram per second. So here comes the MRR. Okay, here comes the MRR. Now the surface of irregularity of electrode used in electrochemical machining pulses are 3 micrometer and 6 micrometer as shown in figure. If the workpiece is of pure iron and 12-volt DC is applied between the electrode, the largest feed rate. Conductivity of the electrode. If conductivity is given, then we can find the specific resistivity of the electrolyte. So 1 divided by 0.02, so it is 5 ohm centimeter. Open voltage, that is drop voltage. Density of iron is given, right? We can write 7.86 gram per centimeter cube. Atomic weight, and you know the valency of iron, that is 2. So here the figure is missing. The figure is missing. I think the figure is what is just like this. In this figure, a nominal gap is given to you. This is a nominal gap. Nominal gap. Nominal gap is given. Now from here to here, the value is 0. or 3 micrometer, and from here to here it is 6 micrometer. So the nominal gap, that is inter-electrode gap, is 3 micrometer plus 6 micrometer, and rest of them is this. Let's say y dash. So y is 9 micrometer plus y dash. 9 into 10 to the power minus 3. Yes or no? Yes or no? Tell me. Tell me. Yes. Zero point zero zero minus 3, right, plus y dash. You can see the value is very small. So can we approximate it as 9 into 10 to the power minus 3 mm? Now we assume the cross-sectional area of the electrode is AC. Okay. Now we need to find the current first of all. So how can we find the current? That is I, or we know that MRR equal to I into E divide by F into rho, centimeter cube per second, equal to cross-sectional area into feed of the electrode. So from here we can find the feed, but we don't know the MRR because we don't have the value of I. So what we do? We are going to find the value of I. So here the value of I, that is I by cross-sectional area into S, V naught minus delta V divide by Y. Now I divide by cross-sectional area, I am assuming it is in centimeter square, and here the value of S is what? 5 ohm centimeter. 5 delta V naught is what? 12 and delta V is 1.5. So 12 minus 1.5. Now here can I write 9 into 10 to the power minus 4 because I have to write in centimeter, right? I have to write in centimeter. Okay, so here the value of I will be what? The value of I, that is 12 minus 1.5 divide by 9 into 10 to the power minus 4. Okay, answer divided by 5. So here 233 and 1 time 3.3 AC ampere. Now here MRR is what? I, that is 2333.3 AC. This is I. And E is what? That is atomic weight 55.85. 55.85 divide by 2. Right. Divide by Faraday constant 96500. Density is 7.86. 7.86. Cross sectional area into feet. Here cross section area will cut out. Answer into 55.85 divided by 2. Answer divided by 96500 into 7.86. So here feet will become 0.0859, but it will be in centimeter per second. So answer into 60, right? And answer into 10. So here feet will become 51.54 mm per minute. Okay, so this is the feet. This is the feet. Clear? Now here the question is of EDM. We have to find time of one cycle in millisecond. So we know that the charging voltage of the capacitor, we not apply voltage 1 minus e to the power minus t by RC. So the capacitor charging voltage is what? Charging voltage is 110, and supply voltage is 20. 1 minus e to the power minus t by resistance is what? Here resistance is, I'm keeping it as it is. So 110 divided by 210. Okay, this comes here 1 minus answer. So here it comes e to the power minus t by RC 0.5. If you take ln on both the side, then 0.693 t by r, that is 40 into 20 into 10 to the power minus 6, right? So answer into minus 1, answer into 40 into 20 in 10 to the power minus 6. So here t 5.545 10 to the power minus 3 minus 4 second per cycle. You can write 0.5545 millisecond per cycle. So option A is the right answer. Clear? Now we have to find the average power input. We know that average power input is half CVC square divided by cycle time. So half C, that is 20 into 10 to the power minus 6. Charging voltage is 1110 square divided by 0.5545 10 to the power minus 3, right? So here 0.5 into 20 into 10 to the power minus 6 into 110 square bracket divide by So it comes out 0.218 kilowatt. So option C is the right one. Is it clear to everybody? Is it clear? Now, the next question. A circular hole of 25 diameter, a circular hole of 25 diameter and depth of 20 machined by EDM process. MRR is given by this, melting point is this, and applied current is this. Machining time we need to find out. So here material removal rate, that is 4 into 10 to the power 4, current, that is 300 into T, that is 1600 to the power minus 1.23 mm cube per minute. So 4 into 10 to the power 4 into 300 into 1600 to the power minus 1.23. So it comes out 1374.4, okay, 01 mm³ per minute. In 1 minute you are removing that much material. So volume of hole, that is pi by 4 d square into h. So pi by 4 d square, that is 25 into h is 20. Here shift pi by 4. Yes, shift pi by 4 into pi by 4 d square, 25 square into 20. So 9817.47 mm³ material get removed. Now machining time is what? That is 9817.47 mm³ divided by 1374.401, right? So answer divided by 1374.401. So here 7.14 minute get used to machine the hole. Is it clear? Is it clear? Okay. Now let's move to the next question. In ultrasonic machining, the material removal rate would increase, decrease, increase, and then decrease, decrease, and then increase with increasing mean grain diameter of the abrasive particle. Increase and then decrease. Remember? Increase and then decrease. In abrasive jet, same question. Yes. Match the following components with the appropriate machining process component: square hole in a high strength alloy, square hole in a ceramic. For ceramic, we prefer ultrasonic machining. So B6, right? And blind hole in a die turbine blade, we use ECM. B3, B6 and D3. B6, D3. So only one option is there where B6 and D3 is there. So option B is the correct choice. Okay, option B is the correct choice. In DC welding, the state polarity result in, state polarity means what? Electrode is negative and workpiece is positive. 30% heat at electrode and 70% heat at workpiece. So heat is less at electrode, so lower deposition rate will take place from the electrode side. Clear? Lower deposition rate will take place. Now in a DC welding process, the voltage in a DC arc welding operation, the voltage arc length characteristic obtained by V of arc is given. V of arc is given where the arc length vary between 5 mm to 7 mm. VR denote the arc voltage, the arc current varied from this. assume a linear power source, linear power source characteristic, open circuit voltage and short circuit current we have to find out. So V of arc equal to V of transformer, right? Because it is the linear power source. So here V of arc V of arc equal to, at L equal to 5 mm. If you put 5 is of 25, so 45 volt, right? And if you put 7 mm here, 7 5 is 35, 35 plus 20, 55 volt. So here 45 volt and 55 volt, we are plotting it on a power source because V of arc equal to V of transformer. So here the line is what? A linear. It means at 55 volt the current is less, at 45 volt the current is high. So less current is 400 and larger current is 500. So this is 0.1, this is 0.2. y2 minus y1 divided by x2 minus x1, y minus y1 divided by x minus x1. y2 is 45 minus 55 divided by x2 is 500 minus 400. y that is v minus y1 that is 55, right? Divide by x that is I minus x1 minus x1. Where is the x1? 400, right? So minus 10, 45 minus 55, yes. Divide by 100, v minus 55 divide by I minus 400. Now it comes minus 1 by 10, v minus 55 divided by I minus 400. Now it is very easy. You know, here the current will 0, so I will 0, right? If I is 0, then minus 400, so 400, okay? Here, at this I is 0, so 400 divided by 10 plus 55. So when I is 0, right, then you will get open circuit voltage that is 95 volt from this equation. And here V is 0, so you will get short circuit current. So V is 0. If you put, then short circuit current is what? That is 950 ampere. Okay, clear? Clear? Now, a DC welding power source has a linear characteristic with an open this. For maximum arc power, the current should be, my dear, for maximum arc power, we know that arc current is half of short circuit current and arc voltage is half of open circuit voltage. So current is 300 ampere. So here 150 ampere is the answer. Okay, very good. Next, during a TIG welding process, the arc, this is basically arc, not a R, this is arc, current and arc voltage is given when in the welding speed is this, and another process, the TIG welding is carried out at a welding speed of this at the same arc voltage and heat input in the material so that the weld quality remains same. The welding current, we know that the heat input equal to arc power divided by welding velocity. In this case, heat input 1 equal to heat input 2. So heat input 1 is what? Power of arc divided by welding velocity of 1, power of arc divided by welding velocity of 2. So Here, what is arc power? That is the voltage 60, that is a voltage 60, okay, into current, that is 50, divide by welding velocity, that is 150, equal to, now the same voltage, that is same voltage, right, same voltage is same, right, voltage is same, and this 120, so here the arc current is, so this cancel, 50 into 120, answer divided by 150, 40 ampere. So here the answer is 40 ampere, right, 40 ampere. Next, here, see, two aluminum plate of 10 mm thick, the thickness is given, that is 10 mm thick and 1 meter long. 1 meter means 1000 mm long, no crowning, and the weld pool is filled by multi-pass, and here the root gap is given, there is no root height. So if no root height, we can neglect this, right? So here this is the root gap, and root gap is maintained at 5 mm. The included angle is 60 degree. So this, right, see, so this is 30 and 30 degree. So we can calculate the cross-sectional area of the weld pool. So here is the cross-sectional area of the weld pool, that is 5 into 10, two similar triangle, okay, plus half. Now plus twice of triangle area, that is half. Now this become 10 of 10 30. So 10 of 10 30, half base into altitude, right, half base into altitude. So 2 cancel. Now 10 square into 10 of 30, answer plus 50, 107.735 mm square. Volume of the weld pool, that is cross sectional area into 1000. So answer into 1000. So 10735.0269 mm cube. Now volume of electrode, that is pi by 4 d square into h. So pi by 4 diameter of the electrode. If the electrode of 5 mm diameter and 500 mm length, so number of electrode pi by 4 into 5 square 500 equal to 10773.0269. So answer divide by 5 square into 500, answer into 4, answer divided by pi. So number of electrode 10.97, approximated 11 electrode. So option C is the right answer. Okay. Next, So we have solved the question in non-stop manner. I hope you people are enjoying, and I hope I haven't wasted a single minute of yours. Did I? No, na? Yes. In arc welding butt joining, the welding speed is to be selected such that highest cooling rate is achieved. Melting efficiency and heat transfer efficiency is given. The area of the cross sectional is 5 mm square. This is 5 mm square. And the unit energy required is 10 joule per mm cube. The power source is 2 kilowatt energy supplying the welding speed. So here, if this is the power source of 2 kilowatt and it is supplying to the energy, transfer efficiency is the melting efficiency 0. And transfer efficiency 0.7. So 2 into 0.7, here 1.4 kilowatt is input, right? And here you are welding. This is the welding speed, right? This is the welding speed. Now the actual heat is what? That is 10 joule per mm square, cross sectional area of the weld pool into welding speed. This is the actual heat, right? This is actual heat. Now the melting efficiency, that is the actual heat, and the heat which you are giving, okay, that is theoretical. That is theoretical. So melting efficiency is 0.5. Actual is what? 10 into AC, that is 5 into V, divide by 1.4 into 10 to the power 3. Now what is the answer? 14. Very good. Option B is the answer. Next. Here a sheet, two metallic sheet each of 2 mm thickness are welded by a lap joint configuration by the resistance spot welding current of 10 kilo ampere. Welding time is this. Spherical fusion zone extended up to full thickness of each sheet is formed. The property of the sheet is given. Contact resistance is this, right? We need to find melting efficiency. So the melting efficiency is actual heat divided by theoretical heat. Simple. So what is the theoretical heat? That is I square RT. I is 10 kilo ampere. R is 500 micro ohm, right? And 10 millisecond. So that much heat will become. So here 10 into 10 to the power 3 square, 500 into 10 to the power minus 6 into 10 into 10 to the power minus 3, 500 joule. 500 joule. Now it is shown that the nugget is forming spherical. The nugget is forming spherical in shape up to full thickness. This is the nugget. So what is the mass of the nugget? That is density into plate into volume of the nugget. So density of the plate is 7000. Volume is 4 by 3 pi. Radius is 2 mm. So 2 into 10 to the power minus 3 cube. So here comes the mass of the nugget, that is 4 by 3 into shift pi into 2 into 10 to the power minus 3, okay, minus 3 to the power cube. 4 by 3 shift pi into 2 into 10 to the power minus 3 to the power 3. Answer into 7000. 2.4, 2.34, 10 to the power minus 4 kg. Now the actual heat, that is mass of the nugget C delta T plus mass of the nugget latent heat. Latent heat is given. So mass of the nugget common C delta T plus latent heat. So 2.345 10 to the power minus 4 C 800 1793 minus 293 1500 plus 300 kilojoule. So 300 into 10 to the power 3. So here answer into 800 into 1500 plus 300 into 10 to the power 3. So here it come 351.85 joule. So what is the melting efficiency then? The melting efficiency is 351.85 divided by 500. So nearby option C will become. Okay, option C will become. Now the next question. Spot welding of two steel sheet of 2 mm thickness. Okay, 2 mm thickness carried out successfully by passing a 4 kilo ampere current of 0.2 second through the electrode. The resulting weld nugget formed between the sheet 5 mm in diameter, assuming a cylindrical shape of nugget, the thickness of the nugget. Here the latent heat of fusion is given, specific heat is not given. Okay, so here melting efficiency is not given, right? If melting efficiency is not given, then we take as 100%. So theoretical heat will be I square RT, right? I square RT. So it is I, that is 4 kilo ampere, 4 into 10 to the power 3 square. R is 200 into 10 to the power minus 6, and time is 0.2 equal to the heat, right? Because if you are assuming melting efficiency is 100%, then the actual heat is what? Actual heat is mass of the nugget C delta T plus mass of the nugget latent heat. But in this question, a specific heat is not given, so just cancel out. Here, what will be the mass of the nugget? That is density into volume of the nugget. So density of the nugget is 8000 into pi by 4 d square, diameter 5 mm in diameter. So 5 into 10 to the power minus 3. 5 into 10 to the power minus 3 square, and HMM. So H into 10 to the power minus 3. Is it clear? Is it clear? So here we are going to put, that is 8000 into pi by 4 into 5 into 10 to the power minus 3 square, H into 10 to the power minus 3. Latent heat is 1400. So 1400 into 10 to the power 3. So can we get the value of H, please? It is what? It is 4 into 10 to the power 3 square into 200 into 10 to the power minus 6 into 0.2. Answer divide by 8000. Answer multiply 4 divided by shift pi. Right. Answer divide by 5 into 10 to the power minus 3 square. Answer divide by 1400. 1 2 3. Answer divide by 10 to the power minus 3. How much is it is coming? 2.9. Good. So 2.9 mm. Okay. Now I think it's the same type of question. Same question. We did it earlier. Now come to NC. In a point-to-point control NC machine, the slides are positions by integral mounted stepper motor driven with the specification of pulse. 1 pulse per right. 1 degree per pulse, and the pitch of the lead screw is 3.6. What is the expected positioning accuracy? इसका मतलब क्या हुआ? What is the meaning? BLU. So BLU is what? Pitch divided by number of pulse for full rotation. So pitch is what? 3.6. Now 1 pulse for 1 degree. So for 360 degree we required 360 pulse. 360 pulse mm. So 3.6 divided by 360. So 0.01. 0.01 mm. Convert it in micrometer. So 10 micrometer. 10 micrometer. Right, 10 micrometer. Is it clear? Is it clear? Now, the next question. Circular arc on the part profile is being machined on a vertical CNC milling machine. CNC part program unit using units with the absolute dimension listed below. N60 G01 X30 Y55 Z-1 G02. The coordinate of the center of the circular arc. अब ये question आप करिए. Do this question. I did lot of question. Right? So it is better that you should do this question. Already I did a lot of question with a super fast speed. Within 1.5 hours, we have done lot of questions. Do you believe that? Within a very small time span, we have done lot of questions. G02 is what? Circular arc interpolation. G01. You are at what position? You are at what position? This is X, this is Y, this is X30. You are at, let's say, X30 and you are at this point. That is X30 and Y55. 30 and 55. Now G02 clockwise like this. x50, okay, x50, so 30, 10, 20, 30, 40 and 50. So 50 and y35, y35 like this, y35 like this. So you are clockwise is like this. So you need to tell the center. So what is the center? What is the center? What is the center? Tell me. What is the center? What is the center? This question I'm not going to do. Now you have to tell me the answer. I'm not going to solve this question. Yes, Aman, 30, comma. Yes, very good. 30, 20, 30 and 55, 20, 35. Very good. 30 comma 30, 30 comma 35. Very good. Because what you have to do, this is a periphery. So basically minus 20. So it will give you 30. Then it is what? It is 35. Then minus 20. It will give you what? Okay. Very good. Now, this question. In a finish machining of an Iceland on a casting with a CNC milling machine, the end mill with 10 mm diameter is employed. Right? 10 mm diameter is employed. The corner point of the Iceland is this. By applying the cutter radius right compensation. Right compensation. You have to tell the coordinates. Right compensation. If you have a doubt, you are typing in the chat a question mark, then my dears, be confident that whatever you are doing is right. This is a workpiece having a coordinate of what? 0, 0 and 0, 30 and 50, 30 and 50, 0. Now right hand side compensation, right? Basically right hand side. So it means what? The tool is placed here, right? And you are standing behind the tool. This is left and this is right. So right hand side means the center will here. Am I clear or not? The center will be here, right? That is minus 5, 5, minus 5, minus 5. Now tool will start from here and it comes here. That is 0, minus 5. Then tool will move from here to here. Tool will move from here to here. I solve these type of question lot of time. This is what? This is minus 5, 55. Then tool move here to here. This is 55, 35. Then tool move here. This is minus 5 comma 35. So minus 5 comma minus 0, I think this 0 comma minus 5, 55 comma, sorry, here it is 55 comma minus 5, right? 55 comma minus 5, 55 comma 35, minus 5 comma 35, minus 5 comma 5. Option B is the answer. How can you say that option A is answer? Lot of time we have done this type of question here, and you are doing mistake at the end. This is not acceptable. Now I'm not doing this question, right? You have to solve. Now tell me the answer. The work table in CNC is driven by a lead screw with a pitch of what? 2 mm. The lead screw is directly coupled with the stepper motor whose step angle is 1.8 degree, right? The number of pulses required to move the table by 50 mm. So it is simple, na? Now tell me the answer. Now tell me the answer. Yes. So for one revolution, we need how much? 200 pulse. 200 pulse. By getting 200 pulse, it moved 2 mm. Or for 2 mm, we need 200 pulse. Then for 50 mm, how much pulse it required? Simple. 5000. Simple. 5000 pulses. Now tell me the answer. A disc. This is outer disc. This is inner disc. This is outer disc. This is inner disc. Tool will move from here to here only, right? So in facing operation, what will be the machining length? What will be the machining length? The outer diameter is 200 mm, right? And the inner diameter is 80 mm. So 100 minus 40. So the machining length in facing is 60 mm, right? Now the feed is given. How much feed is given? 0.1 mm per revolution, but RPM is not given. Here the feed is given, that is 0.1 mm per revolution, but RPM not given. So how can we find the RPM? V equal to pi d n divide by 1000. But here an average or constant velocity, a constant or average velocity is given. So basically this V is V average equal to pi d average into n divide by 1000. So V average, that is how much? 90 pi d average, that is 200 plus 80. 280 divided by 2, that is 140 into n divide by 1000. So what it will be the RPM? 90 into 1000, answer, divide by shift pi into 140. So 204.627 RPM. What is the machining time? That is 60 divided by 0.1 into 204.627 in minute. So here 60 divided by 0.1 into answer 2.93. Option A, 2.93 minute. Is it clear? Is it clear? Next. The shaft of length. The shaft of length 90 mm has a taper portion of 55 mm. The diameter of the taper is 80 and other end is 65. If the taper is made by tailstock set over method, the taper angle and set over respectively. So my dear, H by L equal to capital D minus small d divided by 2L. So what is the set over height? Capital D is 80 minus small d is 65 divided by 2, 55 divided by 90. So 80 minus 65 answer divided by 2 into 55 answer multiply 90. So the set over height is 12.27 mm. Right. Now 80 minus 65 divided by 2 into 55 is also equal to 10 of alpha. Right. So here 10 of alpha. So 80 minus 65 answer divided by 2 into 55. Okay, shift 10 inverse alpha. So here alpha is 7.765 degree. This is half taper angle, right? This is half taper angle. So 2 alpha is what? Answer into twice, that is 15.53. So 15.53, 15.53. Option A is the answer. Clear? Option A is the answer. Okay. Next. Here, in a single drill pass operation, a throw hole of 15 mm diameter is to be drilled set to a plate of 50 mm thickness. Drill spindle speed is 500 feet is 0.2 mm per revolution. Drill point angle is 118. Assume 2 mm clearance at approach and exit. The total drill time. Here, we need to find the total drill time. So we need to find the total length, that is plate thickness plus 2 mm clearance at approach, L2 plus L3 plus L4. L1 is thickness, that is 50. L2 is approach 2. L3 is what? D by 2, that is 15 by 2, 10 beta, that is 59. Right, L4 is over travel. So here you will get the total L 50 to 54. Right, 15 by 2 into 10 of 59. Answer plus 54. So it comes about out 58.506 mm. Is it clear? Is it clear? Is it clear? Now here the machining time is 58.506 divided by F into N. 0.2 into 500 into 60 for second. Answer into 60, answer divided by 0.2 into 500, that is 35.1. Option A is the answer. Right. Next. Here, the length of the workpiece is given, cutter diameter is given, number of teeth, cutter speed, RPM, feed is given, depth of cut is given, total clearance that is entry plus exit is given, that is 5 mm. So the total length is L1 plus approach entry that is x, plus exit, that is y. So here this is given 5 mm. Okay, so L equal to L1, that is 200, A, that is root of small d capital D minus small d plus 5. So 205 plus depth of cut, that is 5, milling cutter diameter, that is 100 minus 5. So here 95 minus 5 root of answer plus 205. Are we doing correct? D, that is, sorry, 2. Yeah, 90, it is not 5. We put a wrong value. Here depth of cut is 2, 100 minus 2, right? Now, so 98 into 2, root of answer plus 205, 249, 249.67. Okay, so the machining time is 249.67 divided by table feed is what? 200. Answer divided by 200, answer into 60. I think this length is somehow we did some mistake. We did some mistake here. We did some mistake here. Yeah, 219, na? Yeah, 219. Yes, we did some mistake. Total length is, that is L plus A, entry plus exit, that is x plus y. So L is 200 and 2 into 100 minus 2, this is 5. 2 into 98, root of answer plus 5 plus 200. Yes, 219. It is 219 mm. Machining time 219 divided by table feed, that is 200 minute. Answer divided by 200, 1.095 minute. He need answer in second. Answer into 60. Answer into 60. 65.7 second. Option B is the answer. Next. Yes. Here 60 cross 30 mm flat surface of a plate is to be finished machined on a shaper. The plate has fixed with a 600 mm 600 mm side along the tool travel direction. If the tool over travel at each end of the plate is 20 mm, average cutting speed is 8 mm, feed rate is 0.3 mm per stroke along the width. The ratio return to, that is a quick return ratio, is 1 by 2. The time for cutting is, here quick return ratio, that is 1 by 2 is given. Total length of machine, that is 600 plus 20 plus 20, that is 640 mm is given. Number of stroke, that is width of workpiece 30 divided by feet per stroke 0.3. So 100 stroke. Now total machining time, right? L into 1 plus m, L into 1 plus m divide by 1000 into V into number of stroke. So L, that is 640, 1 plus 0.5 divide by 1000 into 8 into 100. So 640 into 1.5 divide answer multiply 100, answer divide by 8000, that is 12 minute. So here 12 minute is the answer. Okay, 12 minute is the answer. Next question. For this, I told you a very simple, a very simple relation. This, the relation which I told you in the class, right, work everywhere. That relation will work everywhere, right? I told you here three, I told you the time required to produce one layer in additive manufacturing is first ith layer divided by velocity of the nozzle into diameter of the nozzle plus repositioning time. In this question, ignoring any tool path motion other than those involved adding material and any other delay between layer on separation of the line. So here this is 0. Now here the nozzle diameter is A by 10, A by 10 mm, right, mm, and the linear feed rate A by 5, the velocity is A by 5 mm per minute, mm per minute. Now the thickness of each layer, right, thickness of each layer is, we are considering the diameter, that is A by 10 mm. Clear? Clear? Now my dear, here how many layer we need to produce? It is 1.5a, it is 3a, it is 3a. Now how many layer we required for this part, right? So for this we need to divide number of layer. Here number of layer, that is, let's say n, equal to thickness 1.5a divided by, or divided by a by 10, a by 10, 10, 10, that is 15 layers, right? Total time required, total, that is T1 for part 1, that is 15 into Ti. So 15 into Ti is what? That is Ai divided by Vd. So 15 into Ai, that is 9a square. The cross sectional area is what? 9a square divided by velocity of the nozzle, that is A by 10, A by 10 multiply, sorry, velocity is A by 5, velocity is A by 5 and diameter is A by 10, A by 10. So A square will cancel, 50, 50 into 3 multiply 15. So 225. So the total time will come 2250 minute. Yes or no? Yes or no? Similarly here, the number of layer, let's say n2, this is n1, right? So n2 is, this is a, this is 2a, this is what? 2a. So 2a, so a divided by, so number of layer will be what? 10, because A divide by A by 10. Now total time, that is 10 into AI क्या what is the AI for that? That is 4A square. So 4A square divided by V, that is A by 5 into A by 10. So what is the, that is 50. 50 into 4, answer into 10, that is 2000. Right? Now what is, this is A, this is A. So what is AI? That is A square. This is 0.5A. So what is the number of layer? That is 5 layer. So what is the total time? That is 5 into AI, that is A square divide by A square by 50. Right? So A square cancel, 50 into 5, that is 250. So 250. So 250 plus 2000 plus 2250. Did I? Yes. 6750 for first. Okay. 6750. 50 into 3. Answer into 15. 1.5. How can it possible? 50 into 3. Answer into 15. How a 6? Oh, yes. This is 9A square. Now 50 into 9 into 15. Now 6750. Yes. 6750. So answer plus 2000 plus 250. So total time T1 plus T2 plus T3, that is 9000. Okay. Is it clear? My method is universal. Right. It will work everywhere. Thank you very much.